Hi everybody, Chem 121 students. In this video, I'm going to cover section 6.4, quantifying heat and work, the concepts that are important from that section. Okay, if you have any questions after watching the video, you can email me. All right, if you want me to call you or FaceTime, whatever, let me know that. I have the comments disabled because I want to make sure that your legitimate questions I see right away. All right, I hope everybody's doing fine. And all right, let's get started. Section 6.4, quantifying heat and work. All right. We have this heat equation here, which explains the relationship between temperature change, the mass of an object, and something called specific heat. All right, so let's look here. We have this formula here. Q equals mass, S representative for something called specific heat, which I'll define in a moment, times the change in temperature. Q is the heat released or absorbed. Okay. Its value can be positive or negative depending if it's released or absorbed. Mass, okay, usually in grams. It's always positive. Okay. Here, if it's released, it's negative. If it's absorbed, it's positive. Okay. S is reference to specific heat. Specific heat is the amount of heat required to raise 1 gram of a substance by 1 degree Celsius. Okay. The amount of heat required to raise 1 gram by 1 degree Celsius. I'll write that definition out. And that's positive. Okay, typical units for specific heat are usually joules over grams times degrees Celsius, or little calories over grams times degrees Celsius. Okay, remember specific heat, amount of heat needed to raise 1 gram of a substance by 1 degree Celsius, okay? And then we have this change in temperature here, okay? Change in temperature. Remember, the triangle is the Greek letter delta that's used in science to represent when you have a change in something. It could be a change in heat, change in temperature, change in volume. It's the final minus the initial, okay? It's in degrees Celsius. Change in temperature can be negative or positive, depending if the temperature goes down or the temperature goes up, okay, as it happens in actuality. This can be positive or negative, okay? All right. So specific heat, in your textbook, you have in table 6.4. Specific heat values for different substances. And when you look at that table in the textbook, you'll see that out of all the substances listed, that water has the highest specific heat out of any of those substances listed. Okay, water has a very high specific heat, 4.184 joules over grams times degrees Celsius. Water's very high specific heat makes it useful in a lot of engineering applications where cooling is involved. When you have a nuclear power plant, you have those giant towers, okay? Like if you watch The Simpsons, right? You see these giant things that look like that in the background, okay? They are part of a nuclear power plant. These are the cooling towers. A lot of heat is generated in that process, and you need, and the cooling towers have water which help to absorb that heat. Okay? Cars have water pumps to help absorb some of the energy that's produced in the combustion of the fuel. Okay? And if you think of healthcare applications, you know, if somebody has an extremely high fever, they may do an ice bath in a medical setting to help bring that fever down. So water's high specific heat is something that's you'll see that in the table there, 6.4. All right, let's look at this equation here. Okay, in Chem 110, you've probably seen a similar equation like this and focused more on specific heat. In Chem 121, we're going to do some problems where we solve for heat and for any of the other variables as well. Let's do an example. Calculate the heat required. Remember, heat is a form of energy. Have units that we learned about at our last class meeting. Joules, calories, okay, kilojoules, kilocalories. For this equation we're working with, we're going to see primarily joules. Okay, so calculate the heat required to raise 5.25 grams of water from 5.5 degrees Celsius to 64.8 degrees Celsius. The specific heat of water you may see it as S subscript H2O is 4.184 joules over grams times degrees Celsius. Okay, so we have our heat equation. Q equals mass times specific heat times change in temperature. Okay, well, we want to find the heat. We want to find Q. This is what we want to find. Okay. We have the mass. We have the specific heat. And if it wasn't explicitly stated in the problem, then we would look in table 6.4, such as when you're doing the problems in the back of the chapter that are recommended. Change in temperature, we need to get that number. Okay? So first, I'm going to find the change in temperature. T final minus T initial. Now remember, from and to. We're starting at 5.5 and we're going up to 64.8. Don't always think that one number is final and one number is initial based if it's the lower or the higher number. Remember, temperatures increase and temperatures drop. Pay attention to the words from and to. So we're starting from, 5.5, going to 64.8. This would be your initial, this would be your final. So 64.8 minus 5.5 gives us a difference of 59.3. Degrees Celsius. Okay. All right, now we have everything that we need to plug into the equation. Okay, so the mass is 5.25 grams. The specific heat of water is 4.184 joules over grams times degrees Celsius. And the change in temperature is 59.3 degrees Celsius. Okay, now let's look at that and cancel out units that are the same. What units are the same? Grams and degrees Celsius. That leaves us with units of joules, which are representative of heat units. So if we multiply all of those amounts together, we get 1,302 joules of heat. Okay, now you say, what if we had to put that into significant figures, okay? We have 3 significant figures, we have 4, we have 3. But our measurements are only 3 sig figs for our mass and our change in temperature. If we had to be picky and put this into proper significant figures, we would be forced to put this quantity into scientific notation and have the coefficient with 3 significant figures. Okay, so 1.30 times 10 to the 3rd joules. Okay, that's if we had to be picky with significant figures. Okay, so that's one example where we are finding the heat, okay, that is needed in this interaction here, okay? All right. I know if I were in front of you, I would say, does anybody have any questions? Okay, so if you have questions, make note of your questions, and you can always, with the video, you can go back and, review and all that too. But if you have any questions, you know how to ask me, okay? I'm going to do another example. All right. And I know that these videos are being made because we're not meeting in person. And I know if you were in person, you'd have your notebook and you'd write everything down. You can still do that, okay? Because then when you go to take Chem 122, you still have that notebook. I mean, you can reference that notebook, when you take courses after this course, okay? So it's good to, as I'm teaching it here, you can write it in your notebook, so you have that complete notebook to, in your hands. Let's do another example. Okay. Let's calculate lead's specific heat. Calculate lead. Oops. Hold on. Specific heat. If 57 joules are required to raise the temperature of 35.6 grams of lead, that's a lot of lead, from 25 degrees Celsius to 40 degrees Celsius. Okay. All right, so we have our heat equation. So heat, we have 57 joules of heat. We know that quantity already. We know the mass. We have the temperatures, okay, the starting and the final. Oh, I see there's a glare over here. Oh, I can't fix that. 25 to 40. Oh, there's a glare. Let's see if I can get that out. Okay. All right, first we want to find the change in temperature. So T final minus T initial. Oh, maybe that'll work. Okay. We end up at 40 degrees Celsius. This is a temperature increase. Started at 25. 15 degrees is the difference. Okay. So now we want to find the specific heat. We want to find S. So just like I've been showing you with algebraic equations all along, plug in what you have. If you know in your mind, okay, that you need to find S and you're confident with your algebra, then go ahead and rearrange it. But I'm going to show it with plugging in all the numbers first. Okay, Q equals M. Okay, so we have Q. Mass we have. We all have specific heat. That's what we want to find. And the change in temperature is 15. Okay. So now we need to divide both sides of the equation by 35.6 grams and 15 degrees. So we do the same thing with one side of the equation that we do to the other. Okay, now that will allow for these quantities and units to cancel out. All right, and then we're left with S for specific heat. Now the units for specific heat. Okay, the amount of heat required to raise 1 gram by 1 degree Celsius. So we're left with the units that we need. Okay, now we just need to do the math. So you do 57, divide by the product of 35 times 15. See where I have in blue there? I have the brackets. You got to tell your calculator that you want to take 57 and divide it by this product. Don't just assume that your calculator is going to know that. If you do 57 division 35.6 times 15, you may not come out with the right answer, okay, because your calculator may just divide 57 by 35.6. So make sure that you put in those parentheses there so you tell your calculator what you want it to do. Okay. And you put it into your calculator, all right, and you should get 0.128 joules over grams times degrees Celsius for your specific heat. Okay. All right. All right, we're going to do another problem with specific heat. Okay. All right, this time let's find either the mass or the change in temperature, just so we have enough examples to reference. Okay. A quantity of copper metal absorbs 6,750 joules when heated from 100 degrees Celsius to 451 degrees Celsius. Copper has a specific heat of 0.385 joules over grams times degrees Celsius. You already see how small that is in comparison to water. Okay, what do metals typically do? Metals conduct heat. Okay, not really absorbing it. They're usually transferring it. Okay? They don't hold on to the heat too long. Okay. So quantity of copper metal absorbs this amount of heat when heated from 100 to 451 degrees Celsius. Copper has a specific heat of 0.385 joules over grams times degrees Celsius. Find the mass of the copper metal. Okay. We need to find that change in temperature. Final minus initial. We're starting at 451. I'm sorry, we end up at 451. We started out at 100. Okay, the difference would be 351 degrees Celsius. So this metal is being heated up pretty high. Okay. Remember, metals have high melting points, so you could actually have this happen. All right, so now we need to set up our equation. We have heat. We already have our change in temperature, and we know our specific heat. And again, if it wasn't given to you what the specific heat was, you would look at that table that I referenced. Okay, so we have heat, 6,750 joules. If it were in kilojoules, you would have to convert it to joules because the specific heat is given in joules over grams times degrees Celsius. We don't know the mass, that's what we want to find out. Specific heat we're given, and change in temperature we're given. Okay. We want to get M by itself to find the mass. Divide both sides by specific heat and by temperature. Okay. This cancels, this cancels, cancels, cancels. And we're left with a variable of M for the mass. Now, pay attention to this corner here. Joules cancel. Celsius cancels. And we're left with the units of grams. Okay, when you go to get your final answer, again, remember, take that heat and divide it by the specific heat and the temperature quantities. But remember to put the brackets so you tell your calculator this is what you want it to do. Okay? So in doing that, you should come out with a mass that's 50 grams. I'm not used to having this little small board. You know, I'm used to the 3 big boards in the classroom, so I get adjusted to this a little bit. Okay. All right. And that would be your answer. Okay. All right. The one last thing to mention in this section I was mentioning about the metals, okay, having, you know, they don't hold the heat that long, they transfer it. So let's say we had this copper metal, okay, or some really hot piece of metal, and we put it into a beaker of water, okay? We would have occur is thermal energy transfer. Okay. So you have some heat that is part of a system. So let's say that the system was the copper metal. Okay. Well, that heat is transferred to the surroundings, and it's the opposite value. So if we were to take that copper metal and put it into a beaker of water, then we would have the reverse amount of heat that would be in the water. Okay, the metal becomes colder and the water becomes warmer until they both are at the same temperature, thermal equilibrium. Okay, that would be equivalent to this interaction here. get warmer. Until thermal equilibrium is reached, and both are at the same temperature. Okay. All right. So in one of the labs that you're going to do or see a video of, I don't know how that's going to work for lab, but this was one thing that we would do in the lab for Chem 121. Okay. All right, well, this concludes section 6.4. The next video will summarize sections 6.5 to 6.7, okay, with some concepts there. And then in section 6.8, we will talk about Hess's law. Okay, so that's where we go after this. Okay, if you have any questions about the concepts or the problems in this video, okay, let me know. Okay, I miss teaching in person, but this is what I have to do. So I know the videos may not be super perfect, but you know, trying to get the job done. All right, everybody, take care.